Fariah Jerry, that's who I am. Don't make me say it again. I'm Fariah Jerry, yeah. Okay, so we're back for another video of Gauss's law. And what we're going to do is we're going to look at a point charge in a shell. Now, where we left off with Gauss's law last time is we stated that if we had a surface integral of a constant electric field, or an electric field that was uniform, dotted with some area, that would equal the amount of flux, okay, going through that surface. And what we're going to do this time is this. Let's take a look at a point charge. So here is some positive point charge. Let's just give it a value of Q, okay? Now, I would like to take the electric field of this point charge, and I'd like to move it through some area. And don't forget, this is a dot product here, so it would be very, very helpful for us if that cosine term became 0, which means that I would like my electric field to always be normal to, or to always be parallel to the normal of the actual surface it's moving through, okay? And if I think back to electric fields, I know electric fields for a point charge, they move out uniformly in kind of a spherical shape. Well, not kind of, it is a spherical shape. Poorly drawn by yours truly, okay? So if I could pick a shape to always be parallel, this normal vector be parallel, it makes sense to pick a sphere. Now you might be like, that's a circle, Lord ResTub. Like, no, that's a sphere because we're in 3D. Okay, that's a sphere we have there. And it makes sense that we chose a sphere because if we look at the normal vector to every single point here, you know, our normal vector is pointing up. Our normal vector is like this. So it's a kind of weird way to think about it, but we're always normal to that surface there, which is very nice for us. So what we can quickly do is we can say, look, what is the electric field of a point charge? Well, electric field of a point charge is just KQ over R squared. And then what is the area of a sphere? Well, if you're unaware, the surface area of a sphere is 4 pi R squared, okay? And maybe you've never seen that before, maybe that's new to you. Maybe what you do know is the volume of a sphere. If you know the volume of the sphere is 4/3 pi r cubed, if you take the derivative of your volume, you will get the area. You'll bring the 3 down, that 3 will become a 2. Look at that. And the integral of the area of the sphere, of the surface area, will get you to a volume. This also plays in part with circles. You know the area of a circle is pi r squared, and your circumference is, 2 pi r. Pretty neat, huh? Anyways, that's a side tangent. But yeah, this is the area of a sphere here. So I'm going to get KQ over r squared times the area, 4 pi r squared, and this will equal the electric flux. Well, let's take a look at this. If we rewrite K, and in some prior videos for AP Physics C, we've been rewriting K, and this is the reason why. If we rewrite K, remember K is 1 over 4 pi epsilon naught. Then there's going to be a Q, because that's our Q from above, and then 4 pi r squared over r squared. Let's take a look at this. The r squares wipe, the 4's wipe, the pi's wipe, and the only thing we get is Q over epsilon naught. This allows us to say the following. The electric flux, which is the electric field moving through some surface area on a closed integral, is equal to whatever the charge is enclosed inside of that area divided by epsilon naught. Because that's what we did. We made a surface here, a sphere, we've encapsulated our charge, and then we said, look, the Q here is that charge enclosed. It's inside of our surface, divided by epsilon naught. So this right here, this is the full Gauss's law, and really understanding that that flux is just equal to a charge enclosed inside your shape, whatever it is, divided by epsilon naught is very helpful. Now we're going to try to pick shapes, like I said before, that always allow us to get rid of a cosine theta term. We're also going to try to avoid pointy corners, because what's nice about this shape is that everything is the same value of r away, so that these r's are able to cancel each other out or divide each other out, which is a nice thing. So we don't like cubes as well. So this is all we're doing here. This is Gauss's law, and this is what we're going to run with. And when we come back into our next video, we'll see some more things we can do with spherical charges in this way. But until then, adios, and y'all take it easy.